Good afternoon. Also, in the last class, we started discussing about polymorphism, and we saw that we can achieve it the two ways, either by using function overloading or by function overriding, where the same function name is used to perform different tasks. And when we were talking about function overriding, it is there is one another concept that we want to learn, which is called as dynamic binding. So we saw that when we create objects of two different classes, maybe object of superclass and object of subclass, and when we call the same method, then it will respectively call the method from its own class. Now, sometimes there is a multiple levels of inheritance that can happen. So here they have shown a multiple level of inheritance. So if you have a C1, which is a subclass of C2, C2 is a subclass of C3, and Cn minus 1 is a subclass of Cn. So your Cn is the kind of the parent class of all the classes. And then Cn minus 1 is a subclass of that class, and so on. So this is a, instead of just a single parent child relation, here there is a multiple level of parent child relation. So my Cn is my, maybe if I so here the way they have arranged, C1 is a subclass of C2. So in other words, C2 is a parent of C1, and so on up to n. So let's say there are up to n levels of simple inheritance. And now if we create one object of C1, saying that C1 object is equal to new C1. So in this case, the same method is there in Cn, it is also there in C2, it is also there in C1. Then in that case, it is going to execute the method if it is there in the immediate class. So the object will always invoke a method if it is specific to that class. And if that method is not implemented there, it means it is borrowing whatever method which is implemented in C2. So exactly same way it is going to work. So if that method is not present in C1, it is going to try look that method in C2. So that they have shown it in this direction. If that method is not in C2, it will see if it is implemented in C3 and so on. And if it doesn't find in any of the n minus 1 parents, then finally it has to be there in Cn. If it is not there, then we cannot even call that. So successively, it will look for the implementation for the method. So first it will look within itself if that implementation is not there. If let's say that method is also implemented in C2 and also in C1, then it is going to go with the implementation that C1 has. So the immediate implementation that an object has, it is going to go with that implementation, and that particular property of binding that method to an object of a class and object of a subclass. So wherever the closest binding it matches, that method it is going to execute, and this is called as dynamic binding. Now, why is it called dynamic binding? Because it doesn't know before runtime that actually which method it is going to call. So the compiler, it decides at runtime that whether this method is there or not. So if we are saying C1 obj dot calculate salaries. Now it is going to check, is this method there? Yes, then execute. If it is not there, it is going to look for its parent class. Is it there? Then execute. So the closest one method will get executed. And if it is not there in all of the classes, then it is going to look for the parent of that class. Then if not there, parent of that class. And dynamically it is going to bind. So beforehand, it doesn't know which method is going to get executed and so on. So this is called as the Java virtual machine. It searches the implementation in this order. So the class itself, its parent, and so on. And once it finds the implementation, then that particular first found implementation is. Now, method matching and method binding are two different issues. So we saw that method matching, we generally do it when we are doing it method overloading. So when we are doing it method overloading, we want to know. So if I have one method as, let's say, int add, then in that case, if I'm passing int A, int B, then depending upon the return type and the parameters passed, we decide which method gets executed. And then another method we might have int add, where we might have 3 integers. Another method in which we might have double add, but we might pass floating point numbers and so on. So in this case, the method is distinguished by the method signature, where either the return type or parameter, one of the two things have to be different. And in the same class, we cannot have a method with exactly same return type, same number of parameters, same type of parameter. So out of these three things, at least one thing has to be different, then only we can implement those functions or methods. But in case whenever there is a child parent child relations, we can have exact same method implementation method signature. So the method signature can be same in C1, it can be same in C2, same in C3, and it is still allowed, and it will choose accordingly wherever the implementation is first found implementation. So let's say if the method is implemented everywhere, then it is still going to go with C1. If we created an object of C2, then it is going to implement the method which is implemented in C2 and so on. So here the method need not have different signature. The method might have same parameters, might have same return types. It is still okay for it. But for when we are matching it in overloading, we want at least one thing to be different. So that's the difference between when it happens at compile time. So method overloading happens at compile time. So we are checking is which signature is matching that method we are going to run. And when we are doing it at runtime, then it is dynamically binding. And at runtime, when we are doing it, we don't really know that which method is actually going to get executed beforehand. So again, I think one example here that we are creating new objects. Here, okay, so dynamic. So if you open this program, they have, I think that's the same code. It's the same code. So they have created objects. So I think if you look at the structure here, there is a person class which extends object, and then student class which extends person, graduate student which extends student. So we have object as a parent class, then person, then student, and then grad student. And if we in every implementation we are just going to create the particular string. In class person, it is a person, student, and in object we are toString. We are calling the toString function. And if we are creating the different graduate student, student, person, object, accordingly it is going to call the very first. Now, if you call the graduate student, you will see that the graduate student doesn't have any implementation of that method in the constructor. So in this case, if we don't have that particular toString method implemented in graduate student, then it is going to go to the immediate student class and print student. Then for the next student class, we have the implementation, so it will print student. For person class, we have the implementation again, just it is saying person. And then finally for our object class, Do we have the implementation for object class? Okay, so we are calling it for whichever object you call the toString function. So if we run this program, you will see that it is calling the, for graduate student, it is implementing the method which is implemented in the student class. So in graduate student, it doesn't have its own method. So student class also implements its own method, and person class implements its own method. So here's this method is pretty, you can say, pretty small, but you can implement a more complex method like calculating salary of an employee and so on. So we don't have any more parameters. We will just maybe return the base salary or add base salary plus bonus and so on. Now, another thing we wanted to talk about was its Arraylist class. So Arraylist class, again, it is similar to array, but if we look at the arrays, so we discussed arrays in our previous classes. So I'm going to compare it with Arraylist class. So when we were talking about arrays, so it is already present, so we don't have to really do anything. We have to import this Arraylist class if we are using it, and it is there in java.util library. So if we are using Arraylist class, we have to import java.util.arraylist, and that will import the class. Now, once we have imported, we will use it as a class. So we will use this as a class, and we will create a new object of this class. So we'll say Arraylist A, it's new Arraylist. So whenever we are creating object, we will use the new keyword, and using new keyword, we'll create an object. Now, once we create that object, all the methods which are there for the Arraylist are now accessible to us. So we can add any element, we can add any element to a particular index. So when we just say add element, it adds to the next available position. When we say add at a particular index, so we can add at index 2, we want to add this value. At index 3, we want to add this value and so on. We can clear array list. We can check if that array list contains one element. We can get element at a particular index. We can check index of a particular element in that array. We can check is array list empty. What is the last index of? We can remove. We can check the size of the array list. We can remove element at a particular index, and we can set element in a particular index. So it's very powerful implementation, and luckily we are not really implementing it. So maybe when we start learning more into some data structures like linked list or stack, queue, that time we might want to implement our own. But this array list is already there, and we are just going to use it by importing this particular package. Now, when we were talking about arrays, if you remember, in order to compare it with array, if you remember, array has a consecutive memory. So if we are storing 5 integer values, all the integer values are stored consecutively in the memory. So if it is allowing 4 bytes, so when we say array A5, then it is storing 20 bytes memory consecutively, so that now we can store 5 integer values. In array list, it is not necessarily consecutively stored. So we are storing one integer, then maybe after some time we are storing another integer, then after some time we are storing another integer. So those might be anywhere in the memory. So it's similar to linked list, but it is also following all the properties of arrays. So it is, we can say, best of both. So now we don't have that restriction. So it becomes easy to add and delete intermediate values. We saw that in array, if we remove a of 3, then that value remains empty. So either we push these two values left in order to make it a consecutive array, or we have to make sure that this space is not empty. In this case, if we delete, it will readjust. The array list will readjust, so we don't have to worry about deleting or inserting any new value in this. Then again, another problem with array is that the memory is fixed. So we say that if we have to enter value of 10 students, then we can assign array of 10 students. And if later on, if we have two more students added, then in that case, we have to redefine another array with, let's say, 12 values, and maybe we have to copy all the 10 values which are there into this and get additional 2 values, which is not a very easy task. But since here in array list, the structure is not fixed, we can easily add 2 more nodes into the array list. So programmatically, there are some, we can say, advantages of using array list. Now, if we are using it, so what is the you can say way of using or maybe importing? So my first thing we are going to do is import java.util.arraylist. Now, if you want some more packages from the util library, let's say we are using collections, and in that case we can also say import, let's say java.util.star. If we say java.util.star, it is going to copy all the packages from the util library, and then we are able to use all the classes of the util library. Now, we might not want to do that. So if we are just using a single class, let's say array list, then it doesn't really make sense to import all the classes. But if we are doing more things in a program and we want, let's say, 4 or 5 packages from the same library, then instead of saying those separately, we can just get the whole util library, and that will enable us to use many other things in the util library. Now, if you look at the syntax of writing or importing array list, so you say array list, and here it is the class type. So these are nothing but our data types. So we had classes of different data types. So you saw for integer, floating point, string, and we have to mention which class we want to use, which data type we want to use. Obviously, these data types are all primitive data types. So if we created our own structure, then we are not doing it here directly in the array list. So it will take all the data types which are already there. So the Java knows this data type. So array list string cities. So all the cities we are going to store in this array list, and we have to create an object of this array list. So we are going to say new array list string. Again, the same data type which we are going to create here. Then another thing is, if we can create it pretty much for all data types. So if we are creating an integer array list, we can say array list, and instead of int, now we are using the basic class. So we have to say integer, and maybe I array is equal to new. Similarly, array list, and inside again we will mention that it is integer, and we are creating an object of this array. So let's see, here I believe they have created a string array. So this is again a simple program of creating. So here you can see import java util.arraylist. After that, this is a public class. Then in main, you are specifying that we want to create a city list. So that will be list of several cities, and it is a type of string. So I think Arraylist string, it is of type string and city list. Now we can use different functions that we saw. So add was one function. So when you say city list dot add London, London gets added to that city list at index 0. So again, similar to array, the indexing also starts at 0. So you're saying at index 0, London is stored. Now what happens next? So city list dot add Denver. So at index 1, Denver is getting stored. So how will my list now look like? So initially when I just add London, that list will have London. Then when I add Denver, now the list will have London and Denver. Now third, city list dot add Paris. So now it has 3 cities, London, Denver, and Paris, again stored at index 0, 1, 2. Next, city list dot add Miami. Now it will have 4 cities. Then we are adding another city. So now 5 cities, another city, 6. So total we have 6 cities. One by one we are just writing the list name dot add, list name dot add, list name dot add. Now what are the other things we can do on this list? So if you want to know what is the size of the list, that will be the number of elements in the list. And we have a function which is provided by the Arraylist class is size of the function. So it is essentially, it will have an iterator, it will count all the elements of the list and it will give us the integer value. So in this case, we have 6 cities, so we expect that the number should be 6 here. Is Miami in the list? So how are we going to check? We are going to check with the contains operation. So again, for every data, whenever we are talking about every data structure, we want some basic operations to be done. So that data structure should be able to add some values, search some values, delete some values, give me size of the data structure, and so on. So those are the basic operations of data structure. So every data structure that we are going to consider now onwards. So this is also a kind of a data structure. So whenever we are studying any data structure, we will have to study the operations of what it can do. And these operations are now already given to us. So contains operation again gives us value true if that particular string is a part of that list. Then system.out is the location Denver in the list. So if you want to check what in the list where the Denver appears, so now it should give the city list dot index of Denver. So here, what is index of Denver? Yes, if this is my list, what is index of Denver? 1. Yes, this starts from 0. So London at 0, Denver at 1. So this index we are expecting to get 1. Now, is this list empty? No. So it should give us city list dot is empty should give us false. And if you want to do some more operations, let's say city list dot add at index 2, you add this new city. So now what is going to happen? All the remaining cities after index 2 will get shifted by 1 index. So now Paris was at index 2. Now the new city is, we have mentioned, at index 2, and all the remaining cities will get shifted by 1 index. Now if you want to remove a particular city, we can just say city list dot remove, and it will remove it from the list. Again, when you remove this city, Miami, what is going to happen is the remaining 2 cities is going to shifted to one place on the left, so that the list is never going to have some empty spaces in between, which will be the case if we are using just arrays. But here, if you are removing some cities from any index, it is going to readjust. And in the end, we are going to see a list which is starting from index 0 to size -1 consecutively. So now if we say city list dot remove 1, it should remove the city at index 1. So this is another way how you use remove function in both ways. Either you give the index number or you give the name of the object. So if you say city list remove 1, it is going to remove the city which is at index 1, which is Denver. So next time when it prints, it will print it without Denver. Again, the remaining cities will be shifted one position to the left. And then in the end, if you want to print all the values in the list, either we can just say system.out println city list, that will also print all the strings, or we can use an iterator which goes from I0 to city list dot size, or the reverse order city list dot size -1 up to 0, and we are going to get all the indices and whatever on every index you want to print. Now, if you want to print the list in the reverse order, obviously we have to do it from size -1 to 0 and print it on every index. So this is, I think, circle. So let's see what we get if we execute this. So initially we saw that they are only printing the list size here. So list size, which is at this point, it is 6. Then is city on the list true? So that Boolean value is true. The location of Denver, so which is in index of city, index of Denver, that you get as 1. And is the list empty, that you get as false. Then if you print the list, that will be printed the whole list, or you can print it in the reverse order. Area of circle you can ignore. So this is a simple implementation of list. Now what you can do is you can try maybe for, okay, I will give you that for. So let's continue. So now we can also create a similar list for integer values. So here it is a string. Instead, we can also say integer, and then we can create a list for integer. So what are the different things which we cannot do properly in array, but which are easy to do in array list? So in array, we saw that string A is equal to new string 10. Here we just say we create the object list. And then if we want to get value at a particular index, we can access it. That is easy. Accessing in array is easy. You can just say A and index. Similarly, in list, you say list.getIndex. Then if you want to update something on a particular index, or you want to change a value at a particular index, you can say A of index is equal to London. And in array list, you can say list.set. So get set methods are already defined in that class implementation. We are just now creating an object and we are borrowing those methods. So we can directly use those methods. Now for array, we use the a.len, which gives us size of the array. Here we use list.size function, which gives us size. Now, the other methods that we can perform efficiently in array list, which we cannot perform in array. So adding any element, London, or here, if we reach at 10, we cannot add any more element unless we create a new array. Then we can add at a particular index, London, so that is similar to this. We can remove particular index, we can remove particular object, we can clear the list. So those are some additional functionalities that are available in arrays. So here are some examples. We can also create a string, which is already, or we first create a string as an array, and then we can pass that array as a array list. So where we don't have to now add new elements. So let's say we have a string array containing 3 colors, and then when we create a list of a type string, we are going to pass the already existing array, and we want to use it as a list. Another thing is we can create array of objects from given array list. So meaning passing the object to another function, that is also possible. Then collections, maybe we will see it in the next class, or we can start little bit today's class. So collection is also class, and all of the data structures that we are going to see, linked list, tags, queues, they are all either you can say that subclasses of the collection class. So we can look at all the data structures that we are going to implement. They can look as a subclass of the collection class. So sometimes if we want to use the methods of the collection class, like shuffle, sort, then for that we have to import this class. So if we want to find, let's say in this particular list, we want to find the maximum number, or if you want to find all the elements you want to print or you want to sort. Now here it will sort alphabetically, obviously, but if it is an integer array, it will sort it with its numerical value. Now we can create array list of integers and now passing the same array. So this array, it will be now treated as array list. So now we have array list and we can add, remove, access. So now from the collection class, we can use, let's say, shuffle. So it will randomly shuffle the list and it will change the sequence. And similarly, if we want to sort this list, we can say java.util.collections. So this from the collections class, we can import or we can use the functions to sort. And if we pass the integer list to this, it will sort the list. And now if you print system.out dot print list after sort, if you print the list, it will be in a sorted order. So how will my list now look like? So maybe 3, 3, 4, 5, 5, 6, 15, 34. So we can directly use, so we don't have to use, we don't have to implement the different sorting algorithms here. You can just call it from java.util.collections. And instead of that, you can also again import the collection class. That is also possible. So you can say java.util.collections. That will also allow you to use all the methods. So sort is a very important method. And since everything falls under the collection class, we can use every data structure can use the methods or access the methods which are defined in the collection class. So let's say we are having an add function which add any number up to n. And when we pass that number to add function, so if I say add 1, it's only going to give me 1. If I say add 2, it's going to add first 2 numbers, so 1 plus 2. When I say add 3, it's going to add first 3 numbers. 1, 2. So here you can say that there is now, if you look at all the coming additions, you will see that this part is repeated. So 1 is getting repeated. Now, if you look at 3, you will see that 1 plus 2 is getting repeated. If you look at 4, you will see that 1 plus 2 plus 3 part is common in both of these, and so on. So now in recursion, we will see that there is some repeated part, and that repetition we can do it by calling the same function again. So here, instead of saying add 2 as 1 plus 2, we can also say that add 2 is nothing but add 1 plus 2. So whatever value of add 1 is, if we add 2 to that, then we get add 2. Similarly, for add 3, 1 plus 2 is also nothing but add 2. So we can say add 3 is nothing but add 2 plus 3. Right? Similarly, we can say 1 plus 2 plus 3 is nothing but add 3. So for add 4, we can say instead, we can also call it as add 3 plus 4. And similarly, this part is nothing but add 4. So we can call this part as maybe add 4 plus 5. Right? So here we can achieve whatever is at value n. We can achieve that addition of n by saying you perform addition up to n minus 1 values and add n to that value. That will also give me addition of 1 to n. So if I want to find addition from 1 to n, that is same as finding addition from 1 to n minus 1 plus adding n. So here, in a way, we are calling the same function. If we want to perform addition of 1 to n, we are calling the same function to perform addition 1 to n minus 1 and then add n to that same function. So this is something called as a recursion, where the same task we are getting done by calling the same method, but by using different parameters. So instead of n, now we are passing n minus 1. So we will get the n minus 1 addition, and then we are going to add n to it. Now, similarly, if you look at, so there are certain functions only for which we can do it. So if we are performing a task of, let's say, calculating salary, or if we are doing addition of some numbers, then all problems cannot fit into the definition of recursion. Only if we can see that the problem of solving for n can be broken down into problem of solving n minus 1 and then adding or multiplying some number, then that is a typical example of recursion. Similarly, if you look at the factorial problem, now you might have implemented this. So factorial of 5 is nothing but 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. Again, when you say factorial of 4, it is nothing but 4 multiplied by 3 by and so on. So you can see that the factorial 5, we can also break it down as factorial of 4 multiplied by 5, because that there is a structure where it repeats itself. And whenever we have such a repetitive structure, we can make use of recursion. Factorial of 1 is 1. So in this case, we can also say that factorial of 5 we can calculate as factorial of 4 multiplied by 5. Now, what is factorial of 4? We can break it down as factorial of 3 multiplied by 4. So in other words, I can say 5 factorial is 4 factorial multiplied by 5. Then what is 4 factorial? We can say that is 4 multiplied by 3 factorial multiplied by 5. So this we can say 5 multiplied by 4 multiplied by 3 multiplied by 2 factorial, which is 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1 factorial. Now, this program has to stop when we reach at 1 factorial. So, this is the smallest case where we can calculate factorial, and this is called as a base case in recursion. Now, similarly, whenever we were doing the addition problem, for addition problem, if we are doing it, add n minus 1 plus n, when we actually get a value 5 and we substitute it, so we can say if we have to now go in the reverse direction, I'm calculating add of 5, that is nothing but add of 4 plus 5, which is add of 3 plus 4 plus 5. And when I'm going to stop, when I get to the smallest case, which is the base case. So here I can say add of 2 plus 3 plus 4 plus 5. That is nothing but add of 1 plus 2 plus 3 plus 4 plus 5. Now I should have the value of add of 1 already given to me. So when I substitute that value 1 here, I get the value of total addition of 5 numbers. And same thing we can do here in case of factorial, that you can represent, let's say factorial n is equal to n multiplied by factorial of n minus 1. And till where this loop will go, so it will call its own with giving value 1 less than itself, and it will stop when it reaches to the base case. So base case being factorial of 1 is equal to 1. And the implementation is again pretty straightforward, where you will. Then another similar problem might be Fibonacci series. For Fibonacci series also you can recursively call that function to get Fibonacci series of, let's say, 6. That's also another problem which can be solved recursively. Another problem is Tower of Hanoi. So the Tower of Hanoi problem tells us that how many. So in the Tower of Hanoi problem, there are 3 disks. So sorry, 3 holes, and there are n disks. And the problem says that how many moves we have to make to shift the disks from, let's say this is A, B, C. So if I have some number of disks, so let's say I have here 2 disks, then how many moves are needed to change it to any another hole? Now the thing here is there are certain conditions that you cannot keep a disk heavier than itself on its top. So the arrangement of disks will always be that the smaller disk will be on top of the larger disk. So small disk on large disk. So you cannot keep a large disk on top of small disk. So that is one condition. Another condition is you can move only one disk at a time. So you cannot move 2 disks and keep it on another hole B. So in this case, if you're trying to move the disks from A to B, how many minimum moves will be needed? So that is the equation called as Tower of Hanoi equation. So if you have one disk and if you want to move it, how many moves will be needed? So if you have only one disk and you want to move it from one bar to another, how many moves are needed? So you can move it either to B or C, right? You can just take it and keep it here. So you don't worry much about it. So it is just a single move. Now, if you're moving 2 disks, then I cannot keep smaller disk here and then bigger disk on top of that. So I need one extra bar C so that I can shift the disks if needed. if I have only one bar, then I have to keep bigger disk on top of the smaller disk, which is not allowed. So in this case, I can, in how many ways I can do this or how many moves are needed. So let's say if I move the smaller disk on B, so now this is gone here. Now, once this smaller disk is gone, now A only has the bigger disk. And B has a smaller disk. Now, B has smaller disk. And let's say C is empty. So this is my first move. When I'm moving B from L, I'm moving the smallest disk from A to B. Now, what should be my next move? Sorry, A to C, because this bigger disk I cannot keep it on B, so I will shift it from A to C. So now the biggest disk goes to C. And what is my third move? B to C. So my third move is I'm going to move this small disk on top of C. So how many moves are needed? 3 moves are needed. Now here, if you look at this part where when I'm moving 2 disks, what I did was the smallest disk I moved in 1 move. So when I have 1 disk, that also I moved in one move. And then rest things, what I did was I moved the biggest disk from A to C, and then I changed the smallest disk on top of that. So what they are saying is it is always the moves which are needed. So whatever are the n-1 disks, first we have to move those n- disks to 1 bar. Then you have to move the largest disk from A to C. And then you have to move those many n-1 disks again on top of C. Meaning that if we are talking about H2, the smallest disk, that is my n-1 disk. So once I moved it from A to B, then I moved the largest disk, then I moved the smallest disk back on C. So this is my n-1 disks, moving it from A to B and B to, this is for B to C, and this is for largest disk. So in other words, they are showing it as H2 is H1 plus the larger disk you move, and plus you are moving H1 again. So it is always that twice the number of n-1 disks plus moving your largest disk. So let's say it's not that maybe easy to look into a very small example. Let's now consider we have 3 disks. So if we have 3 disks, now how many moves are needed, do you think? So again, I have A, B, C, and 3 disks. So largest, middle, and smallest. So first, let's say these are A, B, C. I move the smallest disk to B. So that is my first move. Now, once I move the smallest disk to B, my A will have largest and the middle disk. Right? So where can the middle disk go? It cannot go on top of B because B already has a smallest disk. So it can only go, where can it go? It can only go on C. So that is our second. Okay, now after the second disk is gone, now on A, I only have the largest disk. Okay. But the largest disk I cannot keep on B because B already has the smallest disk. I also cannot keep it on C because C also has the middle disk and this is the largest disk. So I cannot keep it on top of either one of them. So what will be my next move? So the smallest disk, you take it and you keep it on top of the middle disk. Because if you keep it back on A, then you are not progressing. You cannot move the large disk unless you have an empty core. So in this case, my third step will be to move it on top of the C. So now you notice now what is happening at C. C has now two disks and my B is empty. B is empty. So now I can move my largest disk from A to B. So here is what they are saying. So every h of n will always be twice, every h of n will always be twice hn minus 1 plus 1 for moving the largest disk from A to B. But before that, we moved the n minus 1 on C. Right now, C has n minus 1 disks and it took me 3 moves. Now, after I move the largest disk on B, I will need the same amount of moves to get it back on B. So once I moved the n minus 1 disks from A to C, now I again need to move those from C to B. So now I'm moving the largest disk on B. And so this is my fourth move. Then what can I do? I have middle and smallest, right? So smallest disk, if I keep here, then I'm not getting the same sequence. So now I will keep the smallest disk on A. So that will be my fifth move. So once I move the smallest disk on A, now I'm going to have a composition where largest disk is on B. A has smallest disk and C has the middle disk. And after this, I'm going to move the middle disk on B. So that will be my move 6. And then finally, I'm going to move the smallest disk on B. That will be my move 7. So again, I can see the equation H3 is equal to H2 twice H2 plus 1. So the number of moves we saw to move 3 disks were 3. Right? Two disks. If I want to move, it takes me three transitions, and here 3 transitions to go from A to C, and 3 transitions to go from C to B back. So total 6 transitions plus 1 transition for the largest disk to go from A to C. So this is also recursive relation, meaning that we can get H3 by knowing H2 and so on. So if you want to find out what is H4, I don't have to see all the transitions now. I can say that twice H3 plus 1. So my H3 is 7. So 2 multiplied by 7 plus 1, that will take me 15 moves and so on. So if you plug in the values, you will get the correct number of moves that the Tower of Hanoi equation will need. Okay, so any problem which can be broken down into a sub-problem of itself, we are calling it as a recursive relation.